going to solve this problem, basically just to practice it. So first we're gonna go through a bunch of um, approaches, and we're gonna discuss the trade-offs of each of those approaches. So let's start with writing this question onto the board. Okay. Okay. So the array that we have is this, or rather the problem that we have. Okay, well, I want this right. Well, that's so weird. Oh, there it is. So here, the array that we have is 1 minus 20 minus 3, 30, 5, 4, and then we are given target. Okay, and we are given an array of integer and integer target. Find a subarray that sums to the target and return the start and end indices of the subarray. And here it is mentioned that this 4 1 is right exclusive, which means the real index where the array ends is 3, but so that's how, like, 4 is not included, but 3 is. So that is something you need to take care of as well. Anyways, so first of all, the brute force way of doing things, right? Let's look at that. How would we do that? So, I mean, if we're going to do the simplest of approach, um, or the least efficient, it might not be simplest, but it's the least efficient. So basically, we are going to generate all the subarrays, right? And then check if the sum of any of those subarrays is equal to this, right? And that's when we return, right? So, we can now that's the kind of thing we can implement, whatever function name. So I think we're gonna need two loops for that. So one loop would, you know what, before moving on to code, let's model this a little bit. So like the first subarray that we can have starting at the 0 index would be this, then the next one would be this, right? So this is like the systematic way of determining uh, all of the subarrays, right? So let's see how many subarrays we got. 1, 2, 3, 4, 5, 6. So we got 6 elements. And then how many subarrays we got? This one is, remember, of size 1. Then 2, 3, 4, 5, 6. So we got 6 subarray. So the size of this thing is n, and also we got 6 subarrays. Okay, and this one is basically subarray of itself, right? This is what I'm saying over here. But could it be subarray of itself? I think it can be. Okay, having said that, now you see we can implement this thing using two loops. Why? You see here 0, this one remains constant, right? And then this index is changing, right? So first we go to 1, then we go to 1, 2, 3, right? So like if I could write those indexes over here, so these are all indexes. So something like this we can implement using for loop, and then we'll do the complexity analysis, which is not going to be efficient, by the way. So we have array length, just writing some JavaScript code. Okay, so the first loop variable will track the starting point, right? And then we have j. Now this is important that we decide. Okay, length, and then we got j plus plus. Where would this thing start, right? Now, what would be the value of j, right? Because j controls the end of subarray, this controls the starting value, right? So we go here. So from this diagram, you can see at one point the ending point is ranging from 0 to all the way to the last index, right? So that would mean that, but ending cannot mm, be something that comes before starting point, right? So that's why we can write I over here, and that's basically going to say mm, that we're going to start with the array of size 1, and then so we're gonna go. So for now, let's say I add a console over here, log, and I'm just logging. So I'm not really capturing like the subarrays, but perhaps we can do that. I just wanted to do the complexity analysis first, just to show you that this is a really bad solution. But still, we should know about that. Okay, so now for the first iteration of this one, when this is at the 0 index, how many times this one would run? This one would run n times, right? This is iterations of inner loop. When this one goes to 1 index, the outer loop, this one runs how many times? N minus 1, right? Because now we're starting from index 1, and if you go from index 1 to the last index, that's n minus 1, right? So you see this thing is decreasing as this is increasing. Now, what would be the last value for this one? Let's try to guess that. What would happen? So when we would be at the last index, the inner loop would run only once. So the value of I here would be 5, and then the j would take the value of 5 and it would run once. That's the end, right? So how many times that would run? It would run once, right? Now we have these terms that represent how many times the inner loop is running, right? Now if we sum those up, right, that looks like a series, right? So we could write it as n minus 1, n minus 2, all the way to 1. Now, how many terms are these? Well, these are n terms. And then, is this the arithmetic series? Well, we can check. We can take this term and then subtract this term, and then we're left with 1 minus 1. So this is an arithmetic I mean, we do need to verify if the, so basically I'm taking this here, subtracting these, what are we left with? Okay, we're left with again minus 1, right? So what is this? This is the difference, also called common difference, right? in arithmetic series. So that tells us this is the arithmetic series. Now we need to find the sum of arithmetic series, and in order to do that, here is the formula. So sum of arithmetic series. But what does that in, arithmetic series represent? That represents the iterations of the inner loop, right? So now n is number of terms, so that's going to be n. 2a. A is the first term, and we know that this is n plus n minus 1 times minus 1, right? So let's solve this one now and see what happens. So when we open this one, it's going to be n plus 1, right? And that leaves us with the n plus 1, and that would be n squared by 2 plus n by 2. Okay, so this is what we're left with. Now, what is the most significant term? That would be n squared. We're going to drop the constant like we do in the big O analysis, and also the least significant term. Now you might ask, why are we dropping? So just to explain, the idea is that this is going to grow faster than this one. This is quadratic, this is linear. So let's have a look at that. So when we are here, okay, this is the graph of quadratic, and then this is the graph of linear function. Now you see, in the beginning, the quadratic line is outperforming the linear one, but that only happens for the smaller values of n. The moment the n is large enough, then you can see the linear is doing better. What do I mean by better? Oh, well, by that I mean for the value of n, if we substitute that in this function, we get a y. Let's call it y1, right? Y1. Let's call it y2. So y1 is always less than y2, right? So this one is always growing faster, and that is evident from the graph as well. And that means we're going to have to do more operations, and this is like an expensive thing, right? This is what this indicates, right? So anyhow, now coming back to the other question, that why do we only care about, somebody could ask, why do we only care about what is in here, right? Why are we only caring about what's in here, all the statements, right? What is inside the inner loop and not outside loop? Well, that is because anything here would have the time complexity of O of n, and that is going to get dropped just like this one. Why? Because it is not the term that has the most impact. It does not. So that's why that gets ignored, and so does the other one, because in the bigger analysis we're only concerned with the something that has the most impact. So anyhow, so this was the analysis. But let's say you're here and you're like, okay, you wanna capture the array, right? That can be a good point, right? So let's say you wanna capture the array. How would you do that? So this one, this I and j are giving us a range. It would be from 0 to 0, then it can go all the way to 0 to n minus 1, you know. So when we wanna iterate over this, right? So we are going to need another loop. And we're going to have to capture this somehow. But I'm wondering, what is it that we want to capture? We just want to get the sum of these, right? Whatever we have over there. Just want to get the sum of this. How would we do that? Well, say, let's start with an example. Let's say you have this 0, 1, 2. Now, how do we do the sum? We're gonna have to iterate from 0 to 1. I'm just wondering how many loops am I going to do? Okay. Let's create a sum variable, and then we're gonna go from k. K would be I. So this would be the starting point, and then we're gonna go all the way to j, k plus plus, and then we're gonna have sum equal to, and we are going to do sum. Okay, that's a mistake. It should be, because this would represent the index that we're reading at the moment, right? So we can say, okay, k. So I'm gonna capture that. And when we are here, we would have the sum. So that's where we need to check if the sum is equal to target, then we return. But what do we return? That's important. So what was the starting point? Starting point was I. And what was the ending point? J. But we need to add one because it is the right exclusive, right? And with that, so let's say the array that we came across is 0, 0, does not have the sum equal to target. Then what's going to happen? This if word run will will be done with this loop. This won't run. Then we'll go back to this loop, right? And first we tried 0, 0. Now we're gonna try, okay, 0, 1, right? And then this loop would basically iterate from 0 to 1, right? So we can also put this thing in a separate function, and we can call it like, okay, do sum, right? It could be a separate function, right? So anyhow, I'm not gonna do that here, but with these two, the complexity was n squared, right? And now with this one, it's going to be n cubed. But how would that be n cubed? Not quite sure. Well, that's how would I do the complexity analysis for something like this? Okay, I'm gonna look into it. But yeah, let me make a note somewhere. Okay. Complexity analysis for nested loop, three nested loop, where third one copies. By the way, the complexity of these outer two is n squared, right? And as for this one runs max n times. Yeah. So I think if that gets multiplied with it, it would become n cube. But yeah, I still would wanna look into rather formal solution for this one. But yeah, this is one way to do it, and this is the brute force. But let's go and have a look at let's have a look at another way, sliding window technique. So that's the one. You wanna next look at that. Okay. I'm not sure I needed to clear that, but okay. Let's see. Oops. Okay. For the sliding window technique, all right. Let's get rid of this. We can start with this one window, right? And then we can check whether the sum of the elements in the window is less than, greater than, equal to what? Target, right? And if it is less than, then we can keep expanding the window, right? So like, okay, keep expanding the window. And when there comes a point when the sum of the window is greater than the target, then of course we don't want that, right? So then we start shrinking like this, right? And if there is a pair, then we'll be able to reach that. Okay, so before we move ahead with implementation, maybe it's a good idea to run an example. Like we have one, right? And then if we expand the window, it's going to be minus 19. Then we expand it further, it's going to be 21, 22, 23. Now it's going to be 22 because in minus 19 we add minus 3. So we expanded a little bit more. Then we expand a little bit more. And what do we get? Minus 22 plus 30, we get 8. Now you see 8 is greater than target. So that's where we need to shrink the window, right? So basically we'll have to check that window sum is greater than target, right? That's the condition that we'll look for. If that is the case, then we start shrinking. But now, how would we shrink? We'll shrink like this. So we'll have a pointer over here, and we'll move that towards right. So that would be like the left pointer initialized to 0 in the beginning, but then we'll move it, right? Okay, having said that, and after doing this, we're going to have to do it in the loop. Why? Because when we're shrinking, we have no guarantee that we are, in reality, we actually have reduced the window sum, right? So what we need to do is that we need to run the loop as long as this is true, because this is not what we seek. That's why we need to shrink the window. Okay, so we keep shrinking the window, and after this loop ends, we check whether the window sum is equal to the target. If it is, then we return the response, because we only care about one. We don't care about like everything. We just need one, right? So let's go to now implementation, and let's do that. So of course we're gonna need left 0. This would represent the start of sliding window. Then we have right. I'm skipping the let keyword just for the sake of brevity. Uh, okay. And then we are gonna iterate to the last index. And then we have, okay, this. Now we need a window sum. I'm just gonna call it sum. And you know what? Let's do it right. Let's call it window sum. And we're gonna have array and gonna add the current element to the window. Okay, gotta initialize window sum to 0. Now, if we're gonna check if when the sum is greater than target. Now, what does that tell us? What that tells us that we need to shrink the window. And how do we shrink the window? Well, in order to do that, we need to remove the leftmost element from the window. So, like, right, no. So, array, right, and then we're like, okay, uh then we need to, no, we need to remove left, not right. That's a mistake. Good thing I caught that earlier. Okay, and then we remove this, remove the left pointer, and there it is. Now when this loop ends right here, this condition will not be true. That means either the window sum will be equal to target or less than. So if it is equal, we're gonna add a check for that. If it is equal to target, then we return, but what do we return? Left. And then what do we return? Right, plus 1. Why do we return 1 plus? Because we want to make the last index exclusive. So that's what we're doing here. And okay, and that's where this loop ends. This one ends here. But now there are like some edge cases we need to think about. What happens if this loop never runs, right? Where is the return statement for that? So we need to leave a return statement here for that as well, just in case if the lead code is testing our solution with the empty array. And what happens if this one doesn't run? Then this one would work. If window sum is not equal to target, then no worries. We'll keep expanding the window in the next iteration. And that's pretty much it. And the type complexity of this solution, since we're going through the array only once, is going to be O of n. And as for the space complexity, well, we are using the constant space, so it's going to be O of 1, right? We only use window sum, and that's pretty much it. Right. Okay, so now we're done with this solution. There is another way to solve this one using the prefix array, but let me just clean all of this first, and then okay, this is rather tedious. Okay, So we can also solve this with the prefix sum array. No, the prefix sum array for this one would have sum from 0 to the I for each of the elements. So like for this one, it's going to be 1, then it's 19, then it's going to be minus 22, then 8, then 9, 10, 11, 12, 13, 17. If I'm not mistaken, yeah. This is what it would look like. Now, let's say we have to find some of this thing. So there are two scenarios for this kind of thing. Our subarray can either be at the beginning or in the middle or extending all the way to end. But the important thing is it starts at the beginning or it starts in the middle. Those are only the two cases that we care about. Right? Now, if let's say we have to find the sum using prefix sum array method, we can quickly do that. Let's say we're standing over here and we want to get the sum of this thing. We can simply check this array, prefix sum array, and we can get the sum right away. And then we also have the access to the indexes and we can return that. But it gets tricky when we are here and now we need to basically get rid of this. We want the sum, but let's say you're standing over here and you determine, okay, this is the array. Now you can't really give the sum from 0 to 4 because that's not accurate. You don't care about 0 to 4, you care about 2 to 4, right? That's what you want, right? So we need a way to get 2 to 4, and turns out there is a formula for that. So we can get, so let's call it I and j. This is I and j. Now the now we need to get this sum, and we do have access to this one. This is cumulative sum, right? So we have 0 to j, and out of that we subtract. What do we subtract? We subtract this one. Now this is I, so what are we subtracting? We are subtracting from 0 to I minus 1 because this is one step before I. So 0 to I minus 1, right? And what is this? This is target. This is what we seek. Now, using this array, we can get the sum I minus 1. And okay, now this is starting to look like two sum question that we have solved often. Okay. Now, it is a key observation. In this I and j, which one would come first? It would be I, right? Because I is the starting point. So I would be less than j, and also I minus 1 is definitely less than j, right? So we could rewrite this thing as sum 0 I minus 1 is equal to sum 0 j minus target. Basically, this came to the right and this came on the other side. Okay. Now, in this equation, we have the target. This is the value that we seek, right? It's a given. And we also have this value, right? Now we can, so basically out of, well, when we are iterating over the array, so this is the array. When we are iterating over the array, we can keep track of the values that we have seen and we can keep track of those in a map. One. So we need to do that. So once we do that, and we can keep track of the index. For now, I'm gonna, well, this count this index as 0, but it will have to be changed as well. So we'll get to that later. I'll explain why. So here we are. Now we have we come across one and we're like, okay, this is the value that we have seen. And that's why we put it in the map and we keep track of the index. So our map is basically the value and the index it was found on, and this is the map data type from uh, object from JavaScript. Now, what happens? Let's say we come across this one, 2, and we subtract, let's say, well, let's say target is 1, right? 2, 1. What would that leave us with? 1. And what does that tell us? Well, that tells us if we are able to find, well, if we already have seen 1, so this says currently you are at 2 and you have seen 1, right? Then that means this formula will be satisfied, and which means we have found a subarray where target condition is being met, right? But here's the thing, this equation indicates that when we are at we're finding, by plugging this 2 in here, we're getting I minus 1, right? So we are getting the cumulative sum of I minus 1, right? So here the index would be I minus 1 as well, right? But we want I. So that's why when we return, we need to do +1 and return that. So we'll do return. So I think that's enough explanation. Let's get to the code. So we're going to need a map. Okay. And then we want to have 0 I less than, okay, we're gonna go all the way to the end of array and then increment, okay. Next we need to check complement. So first we need the sum. This would be the cumulative sum to the point. So, and then we'll be like, okay, for this cumulative sum, do we have something in the map? So we get the complement, then we check the map. Does this has complement? If it does have complement, then we return and we return get complement plus 1, and also the last index that we need to return, right, is going to be I. So I plus 1, because we need to return exclusive index. Now if this isn't true, there is another condition, right? If our array was starting at the beginning, then we can easily find sum. So first we need to check if the target is equal to sum. If it is, then we return 0, I plus 1, right? Then we return that. Apart from that, we need to put this thing, the cumulative sum, in the map. Okay, we put the sum over there, but I think there gotta be one more thing. What would that be? That would be 1, 2, 3. No, what would that be? Well, that's funny. No, it's not. Okay, well, we are going to put the index, the current index. Now, why are we setting this? Because when we set that, in the following iteration, uh, this complement could possibly be equal to this one. And if it is, then we'll be able to detect that using this, right? So as for the edge cases, if this thing never runs, what are we going to do? What are we going to return? Well, if the array is empty, then we return empty. And that's about it. As for the complexity of this thing, the time complexity of this thing is also going to be O of n. As for space complexity, that would be, we're using map, so the map complexity can be O of n, right? If we have distinct elements in the array, then all of them have to be stored, right? So in the worst case, yes, this would be it, and this would be it in the worst case. If we return midway through the array, right, then this won't be applicable, because it's going to be less than, we would not have traveled through the complete array.